Hi, welcome back to the lecture on operations and composition of functions. So let's pick up with composition of functions, or also called composite functions. And let me start with an example so you can kind of get your mind wrapped around why we even need to talk about this. Let's suppose that you make $12 an hour and that you have to pay 15% of your salary towards taxes. So let's think about what is a function that would express our gross income. What is a function that would express the taxes that we owe? And what is a function that would represent our net income? Well, so how can we find our gross income? Right, gross income is what we bring home before we have to pay the government. So our gross income, we'll call that what? G is $12 per hour. So let's say our hours is represented by X. So that would be 12 times the number of hours we work, or 12x, right? So where x is the number of hours. Now, what would be a function for our taxes? So our taxes, we'll call that T of x, is going to be what? 15% of our salary. So we'll say we have to pay 0.15x, where in this case x is our salary. And then what would be a function for our net income? Well, our net income is we get paid our 12x, right? And then we have to pay 15% of that to the government. And so would you agree we'd have to really find 15% of our gross income, which is 12x? And what that's really doing is that's plugging in that gross income inside the tax function. In other words, that is doing T of G of x. Okay, I know that notation looks really weird, but that is saying we're putting in one function into another function. In other words, we're having to make one function operate on another function. And that is what's called composite functions. That is really when we have to substitute one function into another function. So here we can make a definition. If f and g are functions, and the way we write composite is this little circle. So f composed with g, this is red, f composed with g is f of g of x. So what that means is we put g of x inside f of x. Now remember that, it's just like if we had f of 5. We would put 5 in for the x. Well, now we're just going to put g of x in for the f. So we're replacing a whole variable with this whole expression. G of f, or also we can write that as g composed with f, is g of f of x. So this time we would be putting f of x inside g of x. Now when we talk about the domain of the composition of functions, it's kind of confusing, but as long as you'll remember this general rule, you'll get it right all the time. You have to look at the inner function. So in other words, the inner function has to be defined, and then the resulting function has to be defined. So as long as you consider what are the restrictions with the inner function and the final function and find the intersection of those two, then you will have the domain of the composition of functions. So let's look at if f of x is equal to 4x minus 3 and g of x is equal to 2x plus 1, how can we find f composed with g of 5 and g composed with f of 5, and then the composite function that's the general expression for these? So what this would mean to do is to write it like this. So we'd have to think of this as f of g of 5 So what would that suggest that we need to do? Right, we got to work from the inside out. So we need to find out what is g of 5. So somewhere on your scratch paper, let's calculate g of 5. Well, g of 5 would mean 2 times 5 plus 1, which is 10 plus 1, or 11. So g of 5 really is nothing more than finding, well, let me say that out. G of 5 now we're going to replace with 11. So f of g of 5 means really now to just find f evaluated at the function 11. So we're taking what we found at the function g and putting it into the function f. So f of 11 is going to be what? So f of 11 means to do 4 times 11 minus 3. And so that would be 44 minus 3, or 41. Now what about g of f of 5? So that means to do g of f of 5. So now we've got to find f of 5 first. F of 5 is 4 times 5 minus 3, which is 20 minus 3, or 17. So now we're going to replace f of x, or f of 5 rather, with 17. And now we have to take g of 17. So g of 17 means now to replace the x with 17 into the function g. So that's going to be 2 times 17 plus 1, or what, 34 plus 1, which is 35. Okay, so you're always going to plug in to the inner function first, and then the outside function. Now what about when we don't have a number for x, we just want to look at a general expression for what f composed with g of x is. So we still need to think of that as f of g of x. Okay, now don't lose me here. So what I'm going to do is just keep making some substitutions. So we're going to replace, first of all, what g of x is and write out the whole expression. So g of x is 2x plus 1. Right, that's all I did. I just replaced what g of x was, 2x plus 1. Now we want to find f of 2x plus 1. Well, what does f of anything mean to do? If that was just f of 1, we'd have to go to the function f and plug in 1 for x, right? Well, f of 2x plus 1 means we're going to plug inside f this expression 2x plus 1 wherever we see the x. So what is our function f? It says to do 4 times x minus 3. Well, what is x now? It is 2x plus 1. So we would now just simplify this to be what? 8x plus 4 minus 3, which is 8x plus 1. Do you kind of follow what I did? So we're putting the inside function into that outer function wherever we see the x. What about g composed with f of x? So that would be g of f of x. So let's take a look. What is f of x? It is 4x minus 3. So now we're going to plug this 4x minus 3 into the function g. So how do we define g? G of x is 2 times x plus 1. So it's 2 times whatever we're inputting plus 1. So what is our input? Our input is, let me do this in a better color so you can kind of see that. So g is what? 2 times something plus 1. Well, what is that something? It is 4x minus 3. So now we would have 8x minus 6 plus 1, which happens to be 8x minus 5. Now these are not necessarily the same. Just keep that in mind. So the order of that composition is very important in getting your result. Here's another example. F of x equals 3x minus 7, and g of x is equal to x plus 7 over 3. So in this case, what are we doing? That's saying to do f of g of x, which means to do f of g of x, which is x plus 7 over 3. Well, don't worry about what's inside here. Think about the function f. What is it defined to do? The function f is to do 3 times something minus 7. So let's write that out. That's 3 times something minus 7. Well, what is the something? It is x plus 7 over 3. Again, let me do some better coloring so you can see the plugging in. Sorry about that. Okay, f is 3 times something minus 7. Well, our something is x plus 7 over 3. Well, now when we simplify that, notice the 3's divide out. So we're just left with x plus 7 minus 7, which simplifies to be x. Now, let's look at g composed with f of x. So that means to do what? G of f of x, which is g of what function or what expression? Yeah, what is f? That's all I'm looking at now. It's just making a substitution. It's 3x minus 7. So now I'll go to the rule for g. The rule for g says to do this. It says to do x, or whatever you are plugging in, right, plus 7. So it says to do whatever you're plugging in, plus 7, and then divide by 3. So what are we plugging in? We're plugging in 3x minus 7. So if we do 3x minus 7 plus 7, we just get 3x over 3, which is simply x. Well, whenever we have a case where both compositions give us x, that means that the two functions relate in a special way. They are called inverses of each other, and we'll get into that in a later section. But inverses are ones that kind of undo the work of the other function. It's just like if you add 2 and subtract 2, that's inverse relationships. So that is a signal that we have functions that are inverses. But you don't have to understand all that right now. That's not going to be tested at this point. Now, let's look at one more. F of x is equal to the square root of x plus 2, and g of x is equal to x squared. And I want to focus here on the domain. All the others have been linear functions, and the domain of the composite function is just all real numbers. But here we're going to have an example where we don't necessarily have all real numbers. So let's talk about f composed with g of x. Or f of what? F of g of x, right? Which is what? F of, what's g of x? It is x squared. Okay. Now, what is f of x squared? Well, we're going to the function f, right? The function f is defined as the square root of something. Let me go back to my color change. It's the square root of something plus 2. Well, what is that something? It is x squared. So it is the square root of x squared plus 2. So when we talk about the domain, we have to look at the inner function and the outer function and think about any restrictions. Well, the domain of x squared is all real numbers, right? That's a parabola. It's defined for every single value of x. And what about the square root of x squared plus 2? The only place that a square root is not defined is when the inner expression is negative. But x squared plus 2 is actually always positive, right? Because when we square a value, we get a positive number. If we add 2 to a positive number, it stays positive. So the domain of this composition is actually all real numbers. Okay. Now let's talk about g composed with f of x. So that would be g of f of x, which is g of the square root of x plus 2. So what are we going to do here? What does the function g say to do? G says to do whatever you're plugging in and square it. So what are we plugging in? Yeah, the square root of x plus 2. Well, how does that simplify when we square the square root of x plus 2? Do you remember? Yeah, it just undoes it to give you x plus 2. So now we need to think about what is the domain of this function. What is the domain of g composed with f? Well, this is where it's real important. You can't just look at the outer function, or the final function rather, because if I look at the final function x plus 2, it's linear. I might think that it's all real numbers, but that's actually not correct, because what we plug in initially has to be defined. And so the square root of x plus 2 is not defined for all real numbers, right? Because the square root of x plus 2 is the half parabola, or the square root function shifted left 2 units. So the square root of x plus 2 is only defined for values from negative 2 to infinity. So when we look at the inner function compared with the outer, we have to look at what restrictions lie on the inner. There are no restrictions on the outer, so we have to include those restrictions on the inner to get negative 2 to infinity as our domain. Now let me finish up with an application of operations of functions. And this is a business application for revenue minus cost is equal to profit, which is obviously something you would want to know if you were in business for yourself, right? When are you going to make profit? And so an example is this. Fixed cost is $300 and the cost to produce an item is $15. And the selling price of that item is going to be $28. So let's kind of talk about some things for just a minute. Revenue is the amount of money you bring in from sales. Cost is the amount of money you have to pay to produce something. And the profit is what's left over after you take into account everything you bring in and then the money that you have to pay out for producing that item. Okay? So it's the actual money that you make. So when we talk about cost function is always fixed cost plus what we call variable cost. So fixed cost might be rent, right? It's the amount of money that you have to pay regardless of how many items you produce. It's going to always be the same. So our fixed cost in this problem is $300 plus the cost to produce an item, that is my materials, right? And depending on how many things you produce, you've got a cost associated with the number of things that you produce. So we've determined the cost to be $15 per item. So our cost function is 300 plus 15x. Our revenue function is always going to be the amount that you charge per the item times the number of items that you sell. So it is the selling price times the number of items sold. Not selling prime, selling price times the number sold. So in this case, that would be $28 times the number sold, which would be x. So the profit then is going to be P of x, which is going to be the revenue minus the cost. So in this case would be 28x minus, be careful here, we're subtracting off a quantity, so we need parentheses. So we would really have 28x minus 300 minus, what is that? 15x. Or when we simplify, 13x minus 300. So how many items there must be sold to make some money? So if we want to find the answer to this, we need to know, when is our profit greater than 0? So when is that 13x minus 300 greater than 0? Well, we talked about inequalities before, right? We would just solve that by isolating. If we add the 300 and then divide by 13, what is 300 divided by 13? And if we take out our handy dandy calculator, which I don't have on me right this minute, so let me pull up the one online for just a minute. 300 divided by 13 is 23.1. Well, since we don't make a partial item, that would mean that we need to produce 24 items to make a profit, right? How many items must be sold to make some money? So 24 or more would allow us to make a profit. So that would mean if we sell less than 24, what are we doing? Yeah, we're losing money. In other words, the cost to produce those items is exceeding the money that we bring in for those items. Okay, so this concludes part 2 of the lesson on operations and compositions. Be sure to watch the homework video and the calculator video. Thank you.